finishing out Chapter 9. Basically, I want to just review a little bit about gas turbines for propulsion and then do an overview of compressible flow. So we did the jet engine, and when you look at a jet engine, this jet engine is a turbofan engine. But the heart of a turboprop or strictly a jet engine or a turbofan engine is the compressor, the combustor, and then the turbine, and then some exhaust handling. But when you see a big jet engine on a commercial aircraft, it's a turbofan. Well, here's a turboprop. So the jet engine part's right here, true, and it drives a shaft that drives the propeller. And so it's cutting into the air, and there's mechanical power to the propeller. Why do we still have some of these? As I understand it, they're pretty good for fuel economy. And they can go slow. They can go pretty slow through the air. But there's not as many of these as you might think. The more common is a turbofan. There are some excellent YouTube videos that have the dynamics and the rotation and very animated, and it'll show you how a large part of the air goes in this outer ring of the fan and is bypassed. It doesn't go through the compressor. It doesn't go through the turbine or the combustor. But because the fan is kicking it, it comes out much higher speed, and it has definitely a large MDOT, and so that contributes to the thrust. It's just like a propeller, but it's enclosed, and so it's a fan. And then this inner part is usually ingested through the compressor, etc., and goes and also exits at very high temperature, high speed, and significant MDOT. But the combination is to give you a very good thrust, and they're probably the most fuel-efficient engines out there, the turbofans. Now let's move into compressible. There's a couple key things about compressible flow. Let me give you the results. The speed of sound can be shown to be c, that's the symbol for the speed of sound used in this textbook, related to a derivative, how pressure changes with density, assuming isentropic process. That's the basic equation. So c is the square root of the rate of change of pressure with respect to density, holding entropy constant. It's a property relation. One property, speed of sound, is related to other properties, but not just how you add or subtract or multiply. Remember, h is equal to u plus pv. That's clearly how a new property is related to existing properties. But this one, it throws you for a loop the first time you see it, but it's not the multiplying and adding, it's the derivative of, it's the slope of a line. And this line is based on holding s constant. We'll derive that. When you have this relationship, if you assume for air, because we do a lot of calculations with air as the fluid, you find that the speed of sound in air, assuming a constant specific heat, is equal to the square root of kRT. That's a very easy to use relationship. You can calculate the speed of sound in different gases. Typically air is 1.4 if you have a monoatomic gas like helium, right? You're at a birthday party, you don't do this, but you inhale helium and speak and it sounds funny. Well, you're changing the speed of sound in that gas, and then that sounds real funny. But that would be 1.67. Okay, that's the different K for monoatomic gases. And then you have the R, the gas constant, R bar divided by the molar mass, and then the absolute value of temperature. So the higher the temperature, the higher the speed of sound is in an ideal gas. Then we'll talk about the Mach number. The Mach number is the relationship or the ratio of some speed to the speed of sound in that fluid. Often we talk about Mach number flow through air, aircraft going through air. It's traveling at Mach 3, traveling at Mach 8, or 0.8. So these three concepts are important and they basically, when you have sound, it's basically a pressure wave. What you're hearing is a pressure wave traveling to you. So it's compressible effects. Let's do a quick review of how you get this equation for the speed of sound in a gas or in a fluid actually. So the pressure is, the sound wave is a pressure disturbance. So consider a piston, you bump it so it's got a change in velocity, and way ahead of that velocity in a stationary fluid there'll be a propagating front. And that propagating front, that moving front of a wave induced by the movement of that piston, will travel at some speed c. We'll derive the relationship for it. So the quiescent fluid or stationary fluid has enthalpy h, pressure p, density rho, and then behind it, it has a dv, so it has a change in speed. It's now going at the piston speed, and it has h plus dh for the enthalpy, p plus dp, so it's a higher pressure, a larger enthalpy, and a change in the density, rho plus d rho. So take a look at plotting v, velocity, from the face of the piston out. You'll see right where the wave is, there's a jump from zero velocity ahead of it, stationary fluid, to a constant velocity, dv, behind it. Likewise, the pressure, it's some p, nominal p, but then there's a behind the wave, or the front, is a p plus delta p pressure. Consider a control volume enclosing the wave front and riding on it, so you're going at the speed c, you're not accelerating, so you can do, that control volume's not accelerating, but it's moving at constant speed. You see that from the perspective of that control volume, fluid is entering it on the right at speed c with enthalpy h, pressure p, density rho, and leaving on the left at c minus delta v, and then the properties of enthalpy, pressure, and density. Consider a mass balance, so what flows in the left is equal to what flows, out in the left is equal to in the right. You expand out each relationship, it's just rho AV, rho AV. You cancel the areas and you neglect the small change in pressure times the small change in volume. That's neglecting the hot, higher order terms. Two small epsilons multiplied. Maybe in numerical methods you've seen that. You neglect higher order terms. And you're left with this relationship. Go do an energy balance for the same control volume. So you have what comes in the left equal to what, in the right equal to out in the left. Do some algebra, you get dH equal to C dV. Then you use temperature entropy relation, TDS relations that we covered, noting that we're going to consider isentropic disturbance. So it's isentropic boost across that pressure wave. So TDS is 0, but dH is minus VDP. A lot of these pieces of the puzzle, they don't make sense until you put them together, right? So you put these together by combining the mass balance, energy balance, and that thermodynamic relation for entropy being constant, you get C squared is equal to dP d rho, where S is constant, and that's what we set out to show. Take that now and apply it for an ideal gas. What do we know about an ideal gas? Do we know that PV to the K is a constant for an isentropic process? It is. So in other words, you can say P is equal to that constant times rho to the K. Actually, it's P is equal to the constant. Yeah, that's right, rho to the K. If you take the derivative of pressure with respect to density, assuming entropy is constant, you get that constant times K times rho to the K minus 1. Then you can replace that constant by, this constant is PV to the K, or that constant is also P over rho to the K, true? Mass density is inverse of specific volume. And so you replace that constant right here. And then you cancel, and you're left with the PDS is equal to, you have K times P over rho, but it's always an ideal gas, so P is equal to rho RT, or P over rho is equal to RT. You're putting the pieces of the puzzle together. So you can replace that by RT. And now you see that that's equal to C squared. So C is equal to square root of KRT. What's the limitation? It's for an ideal gas. Don't apply it for liquid water.
PV to K, is that somewhere kind of like polytropic?
That's exactly it. Right. And so in chapter 9, I think there's a nice table saying if you have an ideal gas, constant specific heats undergoing isentropic processes, you can relate P and B, P and T, T and V. Yeah, that's exactly right. Now you have the definition of the Mach number, M. Sometimes people put MA, sometimes I might write MA for Mach number, but here we'll just try to be consistent with the book. What does the book use? M. Does the book use M for anything else? Molar mass. So guess what? You got to look at the context. Is that M stand for molar mass or that M for the Mach number? Anyway, that's not too hard to discern. But you have V divided by C. What is the actual speed divided by the speed of sound, or the sonic speed in that air or substance, fluid? If you have subsonic, oh, that's the Mach number is less than 1. And usually if the Mach number is less than about 0.3, there are no compressible effects, even though it may be air. It's just, you can, even for air, you can neglect it and treat it incompressible if it's not going very fast. But as soon as you have air flowing around an object and you're starting to get above 0.3, 0.5, 0.8, you better watch out, because you're having the possibility of some compressible effects not being negligible, because air is compressible. Sonic, that's when the Mach number is 1. Transonic, Mach numbers around 1. See, sonic is right at 1. It could be 0.98. Oh, that's transonic, or 1.03 transonic. It's around 1. Supersonic, greater than 1. And hypersonic is like super, right? So it's the Mach number much greater than 1. Do we actually have some applications out there where you have hypersonic flow? You sure do. Look at the barrel of a tank or the barrel of a weapon, what comes out. They're very fast. Okay. So you can have hypersonic ballistics. As well as somebody was saying, oh, the Department of Defense is trying to have a hypersonic aircraft. And I think they had a test not too long ago that was a little bit of a failure. Yeah, very recent, huh? Blew up. So, but there definitely are supersonic aircraft, right? And for a while, you could fly in them commercially. Go across the Atlantic very quickly, across the Pacific. Now we move on to consider compressible effects, especially in flow in what we call nozzles and diffusers. Beyond that, it's too much. Just can we talk about flow in nozzles and diffusers, both for subsonic as well as supersonic flow. So review subsonic, and this is a hard set of questions, but think about this. I have a nozzle, right? Here's a sketch of it. I'm going to consider its reversible flow. Entropy is constant. I have no irreversibilities in the flow through the nozzle. That's very common. Likewise, a diffuser, but let's get the nozzle down first. Tell me, how is the area of the inlet related to the area of the exit? This is the easiest of the questions up here. Is it that way? Is that the relationship? A1 is greater than A2? Good. Congratulations. Now, what about V? How does the V change from inlet to outlet for a subsonic nozzle, as I've shown, where the cross-sectional area is getting smaller? Does the velocity go up? Is it that way? Good. How about the kinetic energy? Is the kinetic energy of the flow the same in to out? Does it go up or does it go down? It goes up. So it's like this. And what information did you use to discern that? The kinetic energy is 1/2 v squared, and if v went up, v squared went up, true? Now, what about the enthalpy? Somebody would say they're equal, which is a common answer. So now we're back to a 50-50. So you want to do an energy balance. And when you do an energy balance around that nozzle, you find the inlet enthalpy plus the inlet kinetic energy must equal the exit enthalpy plus the exit kinetic energy. Do people follow that line of thought? So now, which way is it? H1 is greater because H1 plus KE1 must be equal to H2 plus KE2. True? And this is larger than this. So this is smaller. This was smaller, this is larger. How's that? To make it still equal. Is this correct? Yes. Temperature. Well, what principle do we use? We know that there's a property. When we talk about ideal gases, and this I forgot to say is an ideal gas, then H is only a function of temperature only. Enthalpy is only a function of temperature. Higher temperature, higher enthalpy. Lower temperature, lower enthalpy. Can I turn it around? Yes, you could say higher enthalpy, higher temperature. Lower enthalpy, lower temperature. Is that right? Yeah. How about pressure? Stays the same. Goes up, goes down. Go down, so is it this way? How do we prove it to a skeptic? How do we prove it to ourselves? We remember for an ideal gas, S is equal to a constant. Instead of PV to the K is equal to a constant, true. You have that other relationship, which, let me quickly turn to it so I don't write it down wrong. That you have, let's say this one, that P2 divided by P1 is equal to T2 over T1 to the power K over K minus 1. S is equal to a constant. Temperature and pressure are related. I think I have it right. Yeah. So, but what happens now? Can you tell? Is the pressure at 2 greater than the pressure at 1? Or is the pressure at 2 less than the pressure at 1? Less. Good. How about the density? Well, the density goes down, so it's like this. Right? Lower pressure, lower temperature, density is going to change too. Okay, let's do this. Switch to a diffuser. Play the same game. Okay, I'm going to consider an ideal gas flow through a diffuser. It's reversible flow, so it's isentropic. I say, what happens to the area? What happens to the speed? True? All of that. Now, when they say a diffuser, what do you expect it to do? It's the nozzle, a lot of people think about it as this. It speeds the flow up. True? Speeds the flow up. What does a diffuser do? Slows the flow down. True? All of this is for a subsonic case. Somebody says supersonic. Did you know that a supersonic diffuser, something that's going to make the flow do what? Speed up or slow down? A diffuser. Flow, slow down, will look like this. It will be, the area is getting smaller. Hold it. That's just opposite of the subsonic. That's exactly right. It is just the opposite of the subsonic. And so when you go to supersonic flow, the diffuser cross-sectional area gets smaller. Okay? So we still have, well, we switch it. So the V, maybe I should have put the nozzle on the left side and the diffuser on the right to be consistent. But you go through the same type of questions here. But before we answer them, let's see, how is this even possible? Well, There's a little bit of a derivation. And after the derivation, you're left with this landmark equation. This equation's in the box at the top. So let's take a look at this box at the top. It says it's a relationship of how changes in cross-sectional area affect the change in the velocity or speed for flow, one-dimensional flow. And notice that this term in parentheses is 1 minus m squared. What is that m? Mach number. When it's equal to 1, it's sonic flow. If it's greater than 1, supersonic. Take a look at what happens to the sign in this term that I just underlined if m is less than 1, subsonic flow. That's our first case. Then that 1 minus 0.3 squared is a positive entity. So if that's positive, then I see that if the area decreases, the speed increases, that negative sign has to be taken into account. All right. If Mach is greater than 1, this term right here is what? 1 minus 1.5 squared. It's a negative. It switches the sign such that if the area goes up, the speed goes up. So if it's supersonic, and you're flowing into a region of increasing area, whoops, it's like this, the speed goes up. It's a nozzle. It accelerates the flow. It's completely contradictory to your first sense, right? But that's the truth. So where does this equation come from now that we see how useful it is? We'd like to see it derived. Okay, well, what you do is you start out and you have the mass flow rates constant through the device. So m dot's equal to rho AV. You go back to calculus where you say a change in m dot's equal to a change in rho and a change in A and a change in V. That's calculus for like chain rule. And then you rearrange. And then you go to the energy equation. You say, you know what? H plus 1/2 B squared. Even if V is changing, H will change, but the sum of the enthalpy and kinetic energy will be constant. You can do the little calculus on that too. You go and find a property relation, a temperature entropy property relation. Say it's going to be isentropic flow throughout. So now I take 1, 2, 3 terms. I bring it to eliminate dH. I go to use a state principle where I express pressure as a function of density and entropy only. A little calculus. I say, hey, I have isentropic process. Scratch that term. So now I have dP is equal to C d rho, C squared d rho. This is very, very similar to the definition of C. It is the same. All those steps are the same. They may look a little different. So you have put it together here, and then you manipulate, bring in this result, and you get, after a little bit of algebra, in following the roadmap laid out in the textbook, you find that you were able to reestablish this equation. But before you get bogged down in the derivation, make sure you can apply it. So when the Mach number is greater than 1, increasing area is a nozzle for supersonic nozzle. It makes it go faster. Well, that's not the only nozzle equation, this one, which we just saw. We also have talk about stagnation enthalpy, and that'll be a symbol H naught. Well, what is a stagnation enthalpy? Well, this term H plus kinetic energy was constant throughout. It's equal to the value as if you brought that flow isentropically to rest, and that would be the enthalpy with no kinetic energy. Stagnation enthalpy. See the term stagnation, brought to rest? Brought to rest enthalpy. If you do bring it to rest, you'll have a corresponding temperature, the stagnation temperature, which will be higher than the other, the nominal temperature at that point when it's flowing with speed V. And so you can relate the stagnation temperature to the actual temperature through this equation. Guess what? I have it on the next slide. It's like the previous derivation. It's a lot of work. And you have the concept of stagnation pressure. So if I bring that flow isentropically to rest, temperature will go up and the pressure will go up. It'll go up to its stagnation pressure, and this is the relationship. So it depends on how fast it is. Does this equation work if Mach number is 0.2, below 1? It does. Does it work if the Mach number is 2? It's supersonic? It does. It works for all of those cases, okay? So this equation worked with Mach number from 0 all the way up, you know, above 1. Same here for this equation and this equation. Here's the derivation. In the interest of time, it's in the book. Is that okay? Here's the derivation. In the interest of time, is it okay? It's in the book. But the concept, what is the concept? It's stagnation. You have to bring it isentropically to rest. Stagnation temperature will be greater than the actual temperature, and the stagnation pressure P naught will be greater than the pressure P. Well, now let's talk about understanding something that's very interesting. So I have a converging nozzle, and I'm feeding it with a supply. So let me sketch. Here is the nozzle section like this, okay? Maybe I'll sketch it a little different. All right? And I'm feeding it from a pretty big supply. And that supply will have a constant pressure that's not going to change, P naught. Hey, you know what? The flow in there is at rest. It's my stagnation pressure. And at temperature T naught. Now, the flow is going to be going through this decreasing cross-sectional area. It's a converging nozzle. See that? And it'll be exiting. Well, when I exit, I want to put it into a large chamber. But this large chamber, I'm going to control the pressure. And this is the illustration the book uses. That's to represent a very large valve. And that valve controls the back pressure in the chamber that it releases into. Okay? So if I wanted to plot as a function of location X, where this location lined up with the exit, okay, from the nozzle, and over here was just, I'm going to plot pressure. So it's P naught way over here, right? Let's say I have the valve closed. What is the back pressure equal to? The same as P naught, flat, pretty boring. No flow. Is the M dot 0? There's no flow through it, true? No flow. But now I open that valve. Maybe it's conceptual. You start with this very high pressure, a couple hundred PSI, 1,000 PSI. And then I open this up to atmospheric pressure. Can you see that thought experiment playing out? You open the valve. So you're going to start dropping this pressure, this back pressure right here. So anywhere over in here, the back pressure is just the back pressure. Okay? But you find that the flow, once it starts to get into this nozzle, kind of right in this vicinity, will do something like that. True? And the exit pressure will be the same as the back pressure. And if I have pressure taps along here, you'll be measuring a decrease in pressure as it goes through the nozzle. True? Let's continue to reduce the pressure. I reduce the pressure. Guess what happens is you get a reduction in the pressure, right? But it goes down, down, down. What do you think the speed is doing as it's going, the gas is going through the nozzle? Going up, up, up. Where do you think the maximum speed is? Right at the exit. True? What happens when it gets to Mach 1? It gets choked. And it's pretty easy to do. It's not hard to do, to get choked flow. Okay? And that happens a lot in practice. So what will happen is it'll get to a point where now if I open this valve some more, the pressure will go down, but it's choked flow right there. It's as fast as it can go by, just air flowing. And so you'll develop a little shock wave which drops the pressure right on the outlet or the exit to that nozzle. Now that shock wave's complicated, and it's not a straight normal shock wave. It's what they call oblique-shaped shock wave. But there's a dramatic irreversibility across that shock wave. Everything else has been reversible flow through the nozzle. And there's a dramatic pressure drop across that shock wave. You can have a dramatic pressure drop or a pressure gain across shock waves. But here you have a shock wave. What happens if I drop that back pressure some more? You're just going to get a bigger shock. You're not going to increase the flow through the nozzle anymore. You're not going to actually change the velocity at any point in the nozzle. It'll have attained. So now that you understand the pressure plot, what you can do is you can go ahead and make another plot, like what is the mass flow rate that goes through that nozzle as a function of the ratio of back pressure to the supply pressure, stagnation pressure. When that's equal to 1, when it's 1, what is the flow rate? 0. But if I open up that valve and drop the back pressure a little bit, the flow rate really goes up quickly. And then it really goes up quickly. And then, but it doesn't go up quickly, and then all of a sudden it's flat. And at this point right in here where it goes flat, that's where it was Mach equal to 1 at the exit of the nozzle. All right? So I can continue to drop the back pressure, and it has no more effect on increasing the flow through it. All right. This pressure that it happens at is P asterisk, the critical pressure, where it becomes choked flow in the throat. Well, once we understand the converging nozzle and how you can get it the maximum flow up to Mach 1 in the converging nozzle, the next question is why can't I get it to go faster than Mach 1? And yes, the aircraft engine that's moving the aircraft at, let's say, Mach 1.5 has to throw gases out faster than that, true? So it's throwing the gases out at faster than that. Well, what you do is you go and you have a converging, diverging nozzle. In the converging section, it's subsonic. In the diverging section, it's supersonic, and now I can get speeds above 1 in the nozzle. All right? So what does the converging, diverging nozzle look like? I'll try to draw the converging section, connect it to a big tank where I have stationary or constant, steady pressure, stagnation pressure, constant, steady stagnation temperature. That's the converging section, true? That's where it's going to be subsonic flow to bring it from rest up to, in the throat, Mach 1. But if I just dead-ended it there, it would be a big shock wave to adjust the pressure. But if I now take it and do this, is that diverging in area? Is it getting big? It is. And this section, you can have supersonic flow that will continue to accelerate and go faster and faster. We gotta maybe not draw it so deep, but that's okay. Let me just draw it shorter. Right here. And then we're gonna end it so that we can control the back pressure with the big valve. Pressure back. Okay, yes, sir.
All right, but if the air when it first exits converging nozzle is subsonic,
We'll cover that.
the Mach is less than 1, right?
Yeah, we're gonna cover that. Let me do it right. Let me do it this way. I'm gonna plot pressure as a function of distance, and I'm gonna try to line up this, try to line up this, and try to line up this, right? So now I start, and I'm going to say that the pressure is at the beginning P naught for all cases, regardless of what the back pressure is. But if I let the back pressure be P naught as well, then what type of flow do I have through the whole thing? Nothing. I have no m dot. M dot 0, true? This is the base case. We start there. Now, you open this valve and you drop the back pressure a little bit. Okay. Is this going to change? No. But what happens is we start to get some flow starting to go faster because it's flowing that way, true? But it doesn't even get close to Mach 1 in the throat. It's all subsonic. And then it maybe reaches a 0.2 Mach number or 0.1 Mach number. What's going to happen when it gets to this increasing area, this diverging section of the nozzle? It's just going to go back up, and then it's going to match the back pressure. So the exit pressure is equal to the back pressure, and there you go. Now the question is the pressure in the throat less than the exit pressure? Yes or no? Is the pressure in the throat, for this case, subsonic everywhere, less than the exit pressure? What's that word? Who ever heard of a venturi? It's in carburetors. Anybody ever see somebody spray paint on an automobile with compressed air? How does the paint come out of the can and get into that airstream? Venturi effect. Go around old aircraft, look at how they have some measurement devices that get wind speed or airspeed, blah, blah, blah. Venturis. If you go and you want to buy some herbicide to spray on your plants, and you use a garden hose, and it has a little jug holding down below it with some herbicide, true, and you turn it on, and after a while, it's drawn out maybe a 1 to 50 ratio, 50 water and 1 of that herbicide. It mixes and sprays it out, true? Venturi, even with water. And so the venturi because it's sped up, the velocity is lower, and then it has a little straw in the carburetor to draw the gasoline out of the bowl up into the airstream in the carburetor, the neck down region, venturi effect. Similarly for the garden hose and spraying the herbicide, so it's very, very common. Very, very common. So yes, that pressure is the lowest right in the middle of the throat, and it's lower than the exit pressure. Now we play where we drop the back pressure some more by opening it up. The exit pressure stays that, and you even get more, like that. True? I've exaggerated to see it good, but that's the venturi effect. But guess what's happening right in here? It's starting to get close to P star, the critical pressure, where the Mach number in the throat is 1. So let's say we drop it a little bit more, and it does hit right there, and now I have Mach 1 right in the throat. Well, let's say it's 0.999 Mach. What's going to happen is it's going to be a subsonic diffuser following the subsonic nozzle. But now let's do it, just drop the back pressure a little bit more. You get to 1, and it now wants to take it and accelerate it some more, because now that looks like a supersonic nozzle, not a subsonic diffuser. The diverging section, up to this point, acted like a subsonic diffuser, this diverging section, but now it acts as a supersonic nozzle. So now it'll come down like this. You'll start to get lower pressure, but if you only reduce the back pressure a little bit, it'll hit a spot and it'll go burp with a shock wave. And the shock then is now across that from supersonic on the left to subsonic on the right. Then it'll act like a traditional diffuser. So up until this point, your area is increasing, the speed is increasing, And after that point, after the shock, it's subsonic. The area is increasing, the speed's decreasing. Let's say you pull it down even more now, right? You continue to open this valve, pull that back pressure down. The shock will move further down because the exit pressure is going down. Let's say you continue off until the shock walks all the way to the exit. And then you can have a shock standing right at the exit. Then you pull it down some more, the back pressure some more by opening that valve, and you'll get a shock that will be not a normal shock inside, but it'll be exterior oblique shock. You pull down the pressure some more, you still get a shock. Then you pull down the pressure some more, but now you have a pressure drop across the shock, not a pressure gain across the shock. But it's very complicated. There's no way we are going to understand one-dimensional analysis will predict those oblique shocks. But there you go. Isn't that interesting? So you could really get the speed of that flow out very high. But let me ask this. We put a plot about the mass flow rate as a function of the back pressure. Whoops, this didn't leave me enough room in here. M dot as a function of PB over P naught. And we start to drop it subsonic. Wow, the flow goes up. But does it do like this when I have a converging diverging nozzle? Or am I able to get a more mass flow out as I continue to drop that back pressure? This is a very tough question. The speed definitely goes up. But think about the flow right at the throat. In all of those cases where I have dropping it and I have a shock here, then shock here, then shock, shock. What's the flow at the throat doing? Is it changing? Am I getting faster flow at the throat? No, it's fixed. And so unless you change P naught and T naught, which we're not, M dot's still flat right there after you get choke flow. So it doesn't change the mass flow rate, but it sure does change the exit speed when you have a converging diverging nozzle. Does that make sense? Does that help? All right. Professor, is this going to be on the exam? No, not really, but I wanted to share with you some things about compressible effects and nozzles and diffusers and this really complicated area. You can spend a whole class and more in compressible effects and propulsion systems and hypersonics. But what I wanted to do to finish today is just solve this problem. So air expands isentropically through a converging diverging nozzle. So it goes like this, then like that. That's a bad looking nozzle, isn't it? Not sure what happened there. So like this. Okay, right here's the throat. And the throat area, and often use an asterisk for the critical pressure, critical temperature, that critical or throat area is 3 centimeters squared. It enters someplace right in here. It's state 1, and the Mach number at 1 is 0.2. The temperature at 1 is 330 Kelvin, and the pressure at 1 is 535 kPa. Assuming ideal gas behavior, good, because we can analyze it using those equations. Otherwise, those equations don't work for water. Water is a poor ideal gas, true? And K is equal to 1.4, which basically is saying constant specific heats, which those analytic expressions were based on a constant K, constant specific heat. Remember those equations? So now they ask, what is the stagnation temperature? It's as if you're saying, I bring this flow 1 to rest, or think about it came from something back here at state 0, which was at rest. P naught and T naught, our big tank. So what is T naught? What is our stagnation temperature? Well, we unravel that equation that I won't flip back to show you, but it was T naught over T, where here I'm going to say T, I know it at state 1, so I'm going to say T at state 1. is equal to 1 plus K minus 1 divided by 2 to the Mach number at 1 squared. That equation that we quickly derived. So you plug in this value of T, 330 Kelvin, this value of Mach number 0.1, square it, and you calculate the stagnation temperature T naught. Is it going to be higher or lower than 330? Higher. 333 Kelvin. What about the stagnation pressure? P naught over P, where I evaluated at 1, is equal to 1 plus K minus 1 divided by 2 times M1 squared. Hey, that equation is exactly the same. Oops. Raised to the power K over K minus 1. P naught is higher or lower than 535 kilopascal? Which one? Higher. So it's 550 kilopascal. What is the exit area? Well, it exits over here at some state 2 where the Mach number is 1.5. True? So it's exiting at a Mach number of 1.5. You take a look at the area equation. Ooh, did I show you the area equation or just, oh, here it is. Area divided by the throat area or the critical area, 1 over the Mach number, 2 over K plus 1. Hey, we're not done with that equation yet. 1 plus K minus 1 over 2 to the Mach number squared. Almost done. All of that raised to the K plus 1 power. Almost done. Don't stop yet. Divided by 2 to the K minus 1. Now, just look at that equation. Do you think it's going to be easy to rederive that? No. But we can use it knowing A star is 3 centimeters squared, and you calculate the area at the exit. The area at the exit 2. Do you think it's larger or smaller than 3 centimeters squared? It's larger. It's going to be larger. 3.56 centimeters squared. Thank you for your attention.